In this video, we take a look at what we call the shell method. So where this comes into play is, let's say we want to find the volume made by revolving a region around a parallel axis of rotation. And the key idea here is that we have a parallel axis of rotation. This is when the shell method is going to come into play. So like I did with the disk and washer methods, what I'll try to do is kind of derive this method for you. It'll give you an idea about where it comes from and how the pieces, parts, and the distances and the shapes come together to give us the volume that we want. Okay, so let's draw a general picture here. Say I've got some function here, f of x, bounded between a and b above the x-axis there. So let's say I take that region and I rotate it about the y-axis, a parallel axis of rotation. Okay, so the region I have is kind of removed from the axis that I'm drawing or that I'm rotating around. And when I say parallel, really what I'm talking about is the strip, all right, the slice. If I draw a slice here, that slice is parallel to the axis that I'm rotating about, okay? So when I rotate that region, I get something, when I rotate the region, I get some three-dimensional figure, and since there's some space away from the axis I'm rotating around, there's going to be a hole in the center of my three-dimensional solid here. When I take the slice, that slice is going to have a thickness of dx and a height of f of x, a height given by the function. So here's about what that shape looks like, and I've tried to draw the slice in there for us. But you'll notice that I definitely don't get a disc when I rotate the slice around, right? And definitely don't get a washer. You know, before we said if there was any space missing, it was a good situation to use a washer method. But here, by drawing a slice that's parallel to the axis of rotation, I get neither a disc or a washer. Okay, so let's try to figure out what shape I actually get here and then see if I can find the volume of the shape I get when I rotate my slice. So here's my figure again. I'm going to take that strip, just focus on that strip in green, and when I rotate that about the y-axis, I get something that looks about like this, right? Just the strip. Now if I keep taking different strips in my region here, and I rotate those, I'm going to get concentric, those cylindrical looking shapes when I rotate each individual slice, okay? That's what integrating will do for me. It'll take all those slices and all those kind of cylinders and stack them inside of one another, okay? But this is definitely not a disc or a washer. What we call this is a cylindrical shell. Okay, and hence the name, the shell method. So what I want to do is I want to try to come up with the volume of that piece that I'm getting. That's this kind of shell of a cylinder. If you kind of think about like a pop can, right? If I could find the volume, not inside the pop can, but just of the material that made up the pop can. That's kind of what you want to think of here. So, like discs, we're going to take the volume of the representative element, take that slice, find its volume or find its area. When we revolve it, then we find the volume of what we get when we rotate the slice, and then we're going to use that to find the entire volume by integrating. Right? So again, if I think of that pop can, or if I think of that kind of Pringles can, basically, I want to find the volume of it. What I would do is cut it right up the middle, and then tear it kind of apart and try to lay it flat. Okay? If you did that with a Pringles can or a pop can, you would just get basically a flat piece of material that would be in the shape of a rectangle. So really what we would get, and I've kind of drawn it more like a box here, but it's a flat piece of rectangular material that has some thickness to it, right? It's not just a flat piece of paper, right? There's actually some thickness there. And I want to describe the dimensions of this. Basically we'll need the volume of the whole thing, length times width times height. It's how we found the volume of a box, right? The height is going to be made up of my function, right? The height of that cylinder, and then the corresponding flat kind of rectangle there, rectangular prism, is the height is f of x, the thickness, the width, if you will, is dx, right? Because that slice is dx thick. And the kind of more difficult part is then the length of this rectangular prism here. That's really made up by what we would call the circumference. The circumference of that kind of cylindrical shell, or of the pop can or of the Pringles can, when you unfold it, that would create the base length, and that would give us our length component of that rectangular prism there. So this is really that circumference. And for us, we would then need some radius. Okay, how do I figure out what that radius is? Well, in the way I've drawn it there, it's basically just going to be the distance from my slice to the axis I'm revolving around, or vice versa, from the axis I'm revolving around to the slice. So for us, that's really just some radius r. And since I've drawn a generic picture, kind of everything with respect to x, when I write down my circumference, it's just going to show up as 2 pi r, 2 pi times that radius, and our radius is really just x units away from the y-axis, x here. So really kind of the most generic form of the shell method, we write that circumference as 2 pi x. And I'll show you some examples later where it's not just x, but really, like I said, the distance from the axis of rotation to your slice, to your representative element. Okay, so we'll come back to that a bit. So I've got the length, the width, and the height now. That will all make up my representative element of volume, dv, length times width times height. And the length is my circumference. My width is my width, and my height is my height, right? My width is like delta x, or dx, I'm sorry, and my height is the function height. So let's write these down in integral form then. When I integrate, I'm integrating from a to b. My 2 pi moves down to the outside. R is going to become x. H is going to become f of x, and w, like I said, is dx. Okay? That's what we call the shell method. Okay? And the way I've drawn it and described it here is kind of particular. I've got some function described as a function of x, bounded so that I just have two x values, a and b, and the region below my curve to the x-axis rotated around the y-axis. Okay, so this is kind of a specific formula, very similar to how I did the disk and washer methods. You have to be flexible here, and I want you to kind of think about, instead of x, f of x, and dx, I want you to think about r, h, and w, radius times height times width. The width is just about always going to be a dx or dy, depends on how our slice is defined or drawn. The height is usually going to be the function. It depends on the region we're working with, and the radius can change depending on the axis of rotation. Okay, let's go through some examples here. First, I want to find the volume of the solid made by revolving the region bounded by this cubic function x minus x cubed, x equals 0 and y equals 0, and I'm going to rotate that region about the y-axis. So kind of similar to my original setup there. I want to draw a picture. And I can do that. I've got a cubic, and I kind of know the end behavior of a cubic function, right? The ends go in opposite directions. It just depends on the orientation of the cubic function. One of the nice quick ways is to find the x-intercepts. So let's do that. Let's factor and set this cubic equal to 0. And thankfully, this factors nicely. I get 3 x-intercepts, 0 and plus or minus 1. So I'm going to plot 0 and at least 1 here. And when I start to sketch, it should have this behavior. The right end behavior should be down to minus infinity because the negative in front of the x cubed, the leading term, is negative. Okay, so off to the left side of there, I didn't give a lot of room to the left of the y-axis, but that's also because this region is going to be bounded by x equals 0. It's bounded by the y-axis. So I don't really care about what's on the left side of that y-axis there, or in the negative x realm. Okay, so let's box those in. I've got bounded by y equals 0, the x-axis, x equals 0, the y-axis. So here is my region then rotated about the y-axis. So I've erased some of that curve that I don't really need. That's the only bit that I'm rotating around the y-axis. Okay, so if I draw a vertical slice, that slice is then parallel to the axis I'm rotating around, and in which case I would want to use shell method. I would get this kind of cylindrical shell. When I rotate that slice around, I've kind of drawn a rough sketch there. It's difficult to draw, but that slice rotated around would indeed give me a shell. So I'm going to try to use my shell method here. The thickness should be dx. The height is going to be my function, right? The height, depending on where I draw that slice, changes by the function x minus x cubed. Okay? So I only then need the radius, the distance from the axis of rotation to the slice, and for me that's going to be x again, right? I'm x units away from the y-axis. Okay, that will change in the next example we do, but I just want to, kind of keep it straight here for a little bit. So again, distance to the axis of rotation from my slice. So let's write that formula then. My dv is going to be 2 pi times the radius, and again that's x for us, times the height of the function f of x times the thickness dx. Okay, so I can write this as 2 pi r h w, right? 2 pi the radius times the height times the width. That 2 pi r is really the length, right? So again, trying to make reference to that kind of general formula of the volume of that rectangular prism. Okay, so from this I have then v, the volume, 2 pi, as long as I integrate. Where am I integrating from here? I'm going to use those x-intercepts that I found, really just from 0 to 1. Right, we already got those. So I have those bounds. I'm moving that slice from x equals 0 to x equals 1, and that's why those bounds are 0 to 1. Okay, I've got the radius x. The function is x minus x cubed. I'll write that in a second here. 2 pi integrate from 0 to 1, x times x minus x cubed dx. If I distribute, I need to integrate this, right? I'm going to distribute my x and get x squared minus x to the 4th. So when I integrate, I get x cubed over 3 minus x to the 5th over 5. So pretty simple antiderivative there. Just evaluate now from 0 to 1. And all I get is when I plug in 1, 2 pi and a 1/3 minus 1/5, which gives me, when I combine fractions and simplify, something like 4 pi over 15. Okay. So a relatively straightforward application of the shell method there. I do have a question though. Why did I not use the washer method here? Why did I not use washer method? I'm going to draw the shape again for us. And if you notice, there's some kind of blank space, right about here. Oops. There's kind of some blank space here. And I said that's usually a nice application for washer method, all right? But for washer method, I would have to draw a horizontal slice, something like this. And I would need then to figure out, the length of that slice as it reaches the y-axis. This would definitely give me a washer when it's revolved around that y-axis, right? Not like the shell I had before. I need the height, right? I kind of need, like, it's easy to say height, but it's really kind of like the length here. Those terms are difficult, but I need kind of this longer radius. I remember I treat washer like 2 discs, which means I would need that length, like my capital R, and I don't even really know how to begin to describe that. If I take my function, I would have to solve it for x. That's pretty difficult. That's a difficult thing to do. In fact, I don't know that I can do that by hand. So this is kind of a really nice setup. This is a really good situation where I would want to use shell method, right? Because that axis is parallel. If I draw a vertical strip to my strip, right? My axis and that strip would be parallel to one another, right? Anytime we can easily draw a slice that's parallel to the axis of rotation is when we would want a shell method, okay? So you've got some decision making to do in these kind of situations. Do I draw a vertical slice or a horizontal slice, and then which shape do I get when I rotate that slice around? Do I get a disc, or do I get a washer or a shell, and which one is easier? If I get a shell, do I have to change a bunch of things? Do I have to look really hard to find the radius or the height? So it just depends on the region you have and that sort of thing. Let's do an example or two here. Find the volume of the solid formed by revolving the region bounded by x equals y squared. So I've got x as a function of y here. X equals 0, y equals 0. That's the x and y axis again. And y equals 1 about, here I've got part A. That's what that A in red is. Part A, I'm going to revolve about the x-axis. So I'm going to draw a picture again, best I can. X equals y squared, I want to graph here first. And that's just going to be a parabola, but it opens to the right, right? Because x is defined by y squared. So I should get some shape that's kind of like this, right? It looks almost exactly like y equals x squared, but it's opening to the right. Okay, so that's x equals y squared. And then I should also draw my x equals 0, my y equals 0, and my y equals 1 shows up about right there. So my shaded region is the region then that I'm rotating about the x-axis in this case. Okay, so things are okay here. I have some blank space, right? And as we've said before, that's usually kind of a nice time to use washer method. If I were to draw a slice that was parallel to the axis I'm rotating around, I would have to, it would be like a dy slice. It would be some chunk of the y-axis. So I would have to keep everything in y. Let's actually try the washer method here instead of shell method, and let's see what happens. So I'm going to draw my slice that when I rotate around the x-axis gives me a washer. So I need then kind of the larger radius and the smaller radius. So the larger one I see there is in yellow, and it's going to have a height of 1. Both of these have a dx thickness, and the smaller radius there is going to be a height given by my function. Okay, but these are dx slices, and that's very important because they're dx. That's going to go at the end of my integral, which means everything inside the integral has to be in terms of x. But my function here is described as a function of y. So I need to convert to functions of x, which actually isn't too difficult in this scenario. But at a time where you have to do something like this, it might persuade you to use a different method where you don't have to convert from one variable to another. Easy enough here. Convert to a function of x. So x equals y squared would then just be y equals plus or minus the square root of x. Because of the way my region is bounded, this is really just the positive square root of x. I don't really need to worry about the negative because of the way this region is. Okay, so I take then the two discs that I get from both of those slices, and I'm going to subtract them. So I need these heights here. The height of the pink slice is the square root of x then. right? That y value is described by the square root function. This other height in yellow is just 1, right? That's got a vertical height of 1. So my integral then, my volume should look like this. It's pi because it's washer method, okay? Integrating, I need to find those two intersection points. And to do that, I need to figure out where my function, the square root of x now, intersects with y equals 1. So I set those two functions equal to each other to set y equal to y, basically y equals 1 equal to y equals the square root of x, and I get then that x equals 1. So I integrate then from 0 to 1, okay? And my slices are moving then kind of horizontally, right? From x equals 0 to x equals 1. The larger radius for me is 1, and I square it, and then I subtract the smaller radius, that's going to be the square root of x, and I got to square that as well. So I see then capital R squared and little r squared. That's my washer method. This all simplifies rather nicely. Pi times the integral from 0 to 1 of 1 minus x dx. And go through the integration rather quick. We end up with pi over 2 as the volume. Okay? So, washer method here, relatively straightforward. The difficulty was converting my functions to functions of x, right? I wasn't given y equals the square root of x off the bat. I was given x equals y squared, so I had to make a change. I had to make a change and make sure everything I was working with was in terms of x so that I can integrate nice and easy and I'm good to go. Okay? What about the shell method? What if we do this with the shell method? Okay? Let's redraw our picture here and see, we should get the same volume, right? I'm rotating the same region about the same axis. None of that is going to change. My volume should still be pi over 2. The method will change, and the way I deal with these distances and the shapes will also change. Let's see if it's any sort of easier or difficult. Here's my picture again. The slice I draw this time should be a horizontal slice. It should be parallel to the axis of rotation if I want to use shell method. Okay? So when I do that, that slice is going to rotate around and give me a shell. Okay? I need the radius. I got to figure out what that is. I need the height and I need the width. The width is going to be a dy width. The height is going to be an x distance. But here x is defined by y squared. Okay, so things are a little confusing here because I'm dealing with x as a function of y. Okay, so I pick a y, I pick a y and I get x from it. Okay, so that distance is actually an x distance, and x should be equal to y squared. That's the function that was given. Okay, that orange distance is the distance to my slice from the axis of rotation. That's my radius. Okay, that's the radius that I'm looking for, and that's a y height. All it is y. Okay, not y equals square root of x, nothing like that. It's just y. So then when I set up my shell method, my volume should be 2 pi integral from a to b of the radius times the height times dy. Now that dy comes from the thickness of my slice, and because it's a horizontal slice, it's some small chunk of the y-axis, so it's a dy slice. Okay, so the way I did this example, I kind of chose a method and then set it up the way I should for that method. Typically what'll happen is you'll have a region and you'll have to decide, does it make more sense for me to draw a vertical slice, a dx slice, and then use either disc or shell or washer, depending on what the radius or the axis of rotation is? Or does it make more sense to draw a horizontal slice? It really depends. I can't really give you kind of a go-to, decision-making, schematic or mechanism. It just kind of depends on the region and the axis you're rotating around. Okay, so I've got the setup of my shell method here. So my volume is 2 pi integral. I still need these two intersection points. but these are going to be y values now. I'm integrating with respect to y. The only confusing part is that they're going to be kind of the same values, right? So my y's here are going vertically from y equals 0 to y equals 1. Okay? Instead of moving from x equals 0 to x equals 1, these slices are moving kind of, vertically up, from 0 to 1. So they're going to be 0 to 1 again. And I know this is the same as it was for the washer method, but I'm looking in a different direction now. I'm looking vertically because my integral is with respect to y. So just be careful with that. Sometimes things will change. The radius is going to be that y height. The height is my function, but my function is described as x equals y squared. So the height should be then y squared. Everything should be in terms of y. The height is kind of on its side, right? It's hard for me to use the word height because the radius was like a height described by y. The purple kind of length, if you will, is what I'm saying describes the height of the cylinder that I would get when I rotate that slice. So you almost have to tilt your head 90 degrees to the right to see what I mean when I say like height. But that's indeed y squared. And the thickness is still then just dy. So this integral simplifies rather nicely. So 2 benefits of using the shell method here. The first is that I don't have to change and figure out what everything is in terms of x when it was given in terms of y, right? I had a function of y. I didn't have to change anything that way. And the integral simplified rather nicely. Now, the other one wasn't all too difficult either, but you're integrating a little bit less here. So there's some advantages to one method over another. In this case, they were probably pretty even, okay? Again, let's verify that this volume matches. We should get a 2 pi out of this. I'm going to get 2 pi times y to the 4th over y, y to the 4th over 4 from 0 to 1. When I plug in 1, I get a 4th times 2 pi is indeed pi over 2. That's exactly the same volume it should be. I've got the same region rotated about the same axis of rotation. Okay, so cool, very cool. Both methods should work the same way or have the same result. It's just one might be a little bit more difficult, some maybe a little bit more confusing to set up. Typically, shell method can be a little bit tricky to wrap your mind around just because now you have to find this extra length measure of the radius, and that can be a little goofy. If I can help explain that a little more, I want to change this example just a little bit. Now, part B, I'm going to try to rotate the same region, but about the line y equals 3. So if you want to pause and make sure you have everything written down, that's good, because I'm going to erase some things here. I'm going to kind of keep a very similar picture, but what I'm going to do is I'm going to erase a bit, put my new axis of rotation up there as y equals 3. My scale's a little off here, but I think you get the idea. So I'm rotating the same region around y equals 3. So some things are going to change here and some are not. Now let's see what happens. I'm still, if I draw that same slice, right, if I still keep my horizontal slice, then what I should do is I should still use shell method because that slice is still rotated then around a parallel axis and it's still giving me a shell. So shell method is still game here. That's what I'll use. 2 pi times the integral. And I got to figure out what I'm integrating here. Pay attention to your slice again, and really the region isn't changing. I didn't change the region, I just changed the axis of rotation. So I should have then the same bounds and really the same height of the function that I did before. Definitely the same bounds from 0 to 1, right? I'm still stacking those slices vertically from 0 to 1, okay? The slice is going to have a kind of a length if you look at it as is, but if you rotate your head, it's got a kind of a height of the function, right? X equals y squared, that doesn't change. But the radius definitely does. That height is 3. So when I figure out my radius, I want to know how far from the axis of rotation my slice is. Okay? The height from the x-axis up to y equals 3 is 3 units. Yeah? The height of my slice up to my slice before was y units. I need the remainder of that, which should be 3 minus y, right? Top minus bottom gives me that distance. That's going to be my new radius. It's the distance from the radius, from the axis of rotation to the slice. Okay, and that slice has a kind of a height or a distance from the x-axis, y units up. So then my new radius should be 3 minus y. If you can dissect those distances, shell method becomes a lot more manageable. Okay, but it's really just trying to focus on what distances am I looking at and how those combine to give me the volume that I want. So I've got my new radius in here. The height, or that h component, the function component, should still be y squared. Okay, that's the height, or that kind of, the height of my slice, if you will. Not how high it is up, but kind of its height, if I were to stand it up. And then the thickness then should still be dy, right? I've still drawn a horizontal slice. It's still a chunk of the y-axis. And when I integrate, I distribute, I get 3y squared minus y. Take the antiderivative, plug in 3y squared minus y cubed, and I get a 3 pi over 2. You can check my work there, but I believe that's correct. That's the volume when I rotate the same region from before, not around the x-axis anymore, but around y equals 3. So in general, when you're rotating a slice around a parallel axis, you're going to be using shell method. Sometimes it's advantageous, sometimes it's not. I've tried to describe a situation where it might be useful, but also show you that the other methods we learned aren't bad either. Right? And they still work. It just kind of depends. Do you want something in terms of X, in terms of Y? Does drawing one slice make more sense in a specific scenario than another kind of slice? And then choose your method kind of accordingly. Okay? Thank you for watching.